morning, students. Today we are going to take module 9 up. We are starting to talk about chemical reactions. This is going to take a few modules. Today we will talk about the types of chemical reactions and we will review solution chemistry. Take page 11 of your lecture notes. There are three types of chemical reactions. First, we have precipitation reaction, in which we are mixing ionic substances that are soluble in water, which upon combination with one another will produce a solid ionic substance that will precipitate out of solution. So for instance here, compare barium chloride will react with potassium sulfate to give us soluble potassium chloride, but a barium sulfate salt that is insoluble in water and will precipitate. In contrast, barium chloride will not react with potassium nitrate, as both potassium nitrate and barium chloride are soluble and will not precipitate. Second type of reactions we will look at are the acid-base reactions, when an acid reacts with a base. In this context, we will focus on acid-base reaction involving proton transfer from the acid to the base. And thirdly, there are redox reactions, oxidation and reduction reactions, that involve the transfer of electrons. So for instance here, the combustion of sucrose is an oxidation reaction. This is a topic that we will not take in that course. It will be taken up in Chem 1050, so next semester for you when you look at electrochemistry. So before we look at precipitation reaction, we need to introduce the concept of electrolytes. There are three types of solutions. First, we have strong electrolyte solutions, in which the solute, it is what we dissolved in that solution, exists entirely as ions. So this will be the case for soluble salts, such as sodium bromide, strontium nitrate, that will fully dissociate into sodium plus and bromide ion, strontium 2 plus and the nitrate ion. And it will be also the case for strong acids and strong bases, such as HCl and KOH, that will fully dissociate into ions, H plus, Cl minus, K plus, OH minus, in aqueous solution. Then we have weak electrolyte solutions. In this case, the species or the compound or the solute that we're looking at is only partially ionized. So that will be the case for weak acids, such as here, acetic acid, HF, HClO, or HNO2, weak acids that will only partially dissociate. Means that most of it will remain as a full neutral molecule, and a little bit will dissociate into an anion and a cation. This will also include those salts that are only weakly soluble, in which you will have some of it solubilizing in water and dissociated, and a lot of it remaining as a solid at the bottom of your Erlenmeyer. And then we have these solutions that are said to be non-electrolyte solution. These are the solutions where we have no ions at all. Either we have a salt that is completely insoluble, that remains solid, or the molecule in question does not form ions. So here, for instance, sucrose will not form ions. If we were in class, I would ask you, can you predict the electrical conductivity of each solution? obviously the strong electrolyte will conduct electricity very easily because the ions will be able to move around from the cathode to the anode. Weak electrolyte solution will be slightly conductive. Non-electrolyte solution will not conduct electricity. Before we move on to precipitation reaction, let us review the diluting of solutions. You will have two types of situations. Type A will be given the dilution information. You will have to calculate the exact concentration of molecules or ions present in the dilute solution. Case B, you will be asked to provide a precise recipe to dilute a solution of known concentration to make a more dilute solution with a precise concentration. Let us look at an example of case A. Here you're asked, what is the molar concentration of strontium ion in a solution prepared by adding 25 milliliters of 0.2346 molar strontium nitrate to 275 milliliters of pure water? Strontium nitrate is fully soluble in water and dissociates into strontium 2+ and nitrate ions. When you look at the stoichiometry, 1 strontium nitrate gives 1 strontium 2+, and it's very important to pay attention to this stoichiometry because if your question was on nitrate, you will have to consider that it gives 2 nitrate ions. So what you can say is that the number of moles of strontium ion is equal to the number of moles of strontium nitrate in your initial solution. You can also write it as the molarity of strontium ion is the same as the molarity of strontium nitrate, even though this is now a nominal concentration since you don't really have strontium nitrate in solution. It is fully dissociated. We need to make a side note here. Concentration are also defined with the letter C, CXX, for a concentration given in any unit. When we have this MXX for molarity, it means that the unit is in mole per liters. It's a molar concentration, so we'll use the unit M. So what do we have? We have an initial volume, 25 milliliters, of initial molarity in strontium ion, 0.2346 molar. We add 275 milliliters of water, and we end up with a final solution of volume VF and concentration that we need to calculate. The final volume is, of course, 25 plus 275, 300 milliliters. What we have to recognize is that the number of moles of strontium ions in the initial solution is the same as the number of moles of strontium ion in the final solution. We just added water. So this initial number of moles is given by the molarity initially times the initial volume, and the molarity of the final solution in strontium ion can be related to the final volume and the number of moles of strontium ion. So we can write this number of moles equals this number of moles. So we can write this equation. If we rearrange over what we're looking for, which is the final concentration of strontium ion, we get the initial concentration times the initial volumes divided by the final volumes. Plug in the number. This is what you get. What you see here is that we have mole per liters, liters and liters. So these two units will cancel each other, meaning that we could have left 25 milliliters over 300 milliliters to still get a concentration in mole per liters or a molar concentration. If you do the calculation, you will find that the molar concentration of strontium ion is 0.01955 molar, and the concentration of nitrate ion would be 2 times that of the strontium ion, since we have 2 nitrates per strontium nitrate, so it will be 0.03910 molar. As usual, pay attention to the sig figs. Here we have 4 sig figs, like we had here and we had here. Example 2, taking an example of case B. Supply a recipe for making 5 liters of 0.01234 molar sodium hydroxide solution. You have access to a solution of sodium hydroxide in water made by adding 45.67 grams of sodium hydroxide to 2 liters of water. So let's see what we have. We have an initial solution of sodium hydroxide made by dissolving 45.67 grams of sodium hydroxide in 2 liters of water. We take some of this, we add water up to 5 liters to get a solution, 5 liters of a solution with a molarity of 0.1234 molar. First thing we need to do is calculate the molarity of our initial solution. How do we do that? We know that the molarity of our initial solution is defined by the number of moles of sodium hydroxide over the initial volume. And we can calculate the number of moles of sodium hydroxide by dividing the mass or weight of sodium hydroxide, 45.67, by the molar mass of sodium hydroxide. In an exam setting, you have to go and calculate the molar mass of sodium hydroxide using your atomic mass given on the periodic table data sheet. So it's going to be 22.99 plus 16, it's oxygen, plus 1.01 is hydrogen, 40 grams per mole. So then we can calculate the number of moles of sodium hydroxide, 45.67 divided by 40, and relate that number of moles over the volume, giving us the concentration of our initial solution of sodium hydroxide, 0.5709 molar. Then we need to figure out how many moles of sodium hydroxide do we need in our final solution. We know that we want 5 liters of this final solution, and we want a molarity of 0.01234 molar. So the number of moles of sodium hydroxide in our final solution can be calculated by the final concentrations or molarity times the final volume. This number of moles of sodium hydroxide is provided by our initial solution. So the question is, what is the volume of initial solution that contains this number of moles of sodium hydroxide that we want in our final solution? So we can also calculate this by using the same equation. This number of moles times the initial molar is the initial molarity times the initial volume. This is what we're looking for. These numbers of moles are equal, so we can write this equation and rearrange it so that we find the initial volume of solution that we need. It's going to be the final molarity times the final volume divided by the initial molarity. If you plug in the numbers, you will see that the volume of initial solution that you need is 0.1081 liters or 108 milliliters. So the recipe will be, to a 5-liter volumetric flask, we add 108 milliliters of the concentrated initial sodium hydroxide solution. Then we add enough water to bring the volume up to the mark on the volumetric flask. We seal and we shake. We are going to talk now about solubility and precipitation reaction. Based on observations, the following rules allow us to do qualitative predictions. If a substance has a solubility that is less than 0.01 mole per liter, it will be considered insoluble. If a substance has a solubility that is greater than 0.1 molar per liter, it will be considered soluble. If a substance has a solubility between 0.1 and 0.001, it is considered sparingly soluble. Based on these experimental observations, solubility rules have been established. So we have 7 rules. These rules will be given to you on your midterm data sheet. But if you look at it, it's next page in your note, you will see that the structure of the salts are not given. So you need to know the structure of the various salts and the polyatomic ions. Those are given to you in the must-know file on CourseLink, as well as table 2.6 in your textbook. So what are those rules? Rule number 1. All alkali metals group 1A, which is lithium, sodium, potassium, first column in the periodic table, as well as ammonium salts, NH4+, will be soluble. Rule number 2, all nitrates, acetates, chlorates, and perchlorate salts are soluble. This is where you need to know the structure of these polyatomic ions. Rule number 3, most chloride, bromide, and iodide salts are soluble, except halides of silver plus, halides of lead 2+, or halides of mercury 1. Mercury 1 is a weird salt. It's a binary salt. Instead of being mercury plus, it's mercury 2 2+. As well as mercury 2 bromide is insoluble, and mercury 2 iodide is insoluble. Rule number 4, most sulfate are soluble except for silver sulfate, lead sulfate, mercury 1 sulfate, calcium sulfate, strontium sulfate, or barium sulfate. Now for those insoluble salts, most carbonates, phosphates, and oxalates are insoluble, except those of group 1 and ammonium. This is rule number 1. Hydroxides, oxides, sulfides are also insoluble, except again those from group 1A and ammonium salts, rule number 1, and hydroxides and sulfides of group 2A, calcium, strontium, barium, which are a little bit soluble. Chromate salts are insoluble, except, once again, those from group 1A and ammonium from rule number 1, as well as chromates of calcium and magnesium. Doing an example of question that you may be facing. Use the solubility rules to predict the solubility of the following compound. A is silver bromide. So here we can look at rule number 3. Most chloride, bromide, and iodide salts are soluble, that's bromide, except for silver, lead, and mercury halide. This is silver bromide. Therefore, it is insoluble. Rule number 3. Silver perchlorate. I look at my table. All nitrates, acetates, chlorates, and perchlorate salts are soluble. That is rule number 2. This is silver perchlorate. There is no exception noted in rule number 2. Therefore, it is soluble. Then we have mercury bromide. Mercury bromide, I go back to my rule number 3. Most chloride, bromide, and iodide salts are soluble except for silver, lead, or mercury 1 halide. This is a mercury 1 halide, therefore it is insoluble. Rule number 3. So this concludes Module 9 on chemical reaction. Go and take activity number 9 as well as textbook questions. Make sure that you review your polyatomic ions. It will be very important that you know those. Bye now.